Hello everyone, welcome to my YouTube channel Advanced Physics with Biplav Dhar. Today I have come up with a very interesting question from the chapter Thermodynamics, or you can say it's from the chapter Kinetic Theory of Gases. I have touched a important topic that is not widely covered in our class, but anytime JE Advanced can ask this type of question. So let's go to the question. Uh, an ideal gas of density rho is kept inside a cubical container. The gas molecules move along all the directions randomly, but x component of its velocity has a hypothetical distribution curve as shown in the figure. Fx dvx is the fraction of molecule in any volume moving with velocity vx vector to vx plus dvx vector. So this is a hypothetical velocity distribution graph of a gas sample. So by this time, you have read the question statement. You have guessed that it is a question from Maxwell-Boltzman velocity and speed distribution graph. And so in your course, if you have studied this velocity and speed distribution graph properly, then you can definitely solve this question. What is important not to remember the equation of that velocity or speed distribution graph of Maxwell-Boltzmann, but you need to understand thoroughly that how this graph helps us to determine different velocities, and also how the speed distribution graph helps us to find the pressure at any particular surface of a container. So this question is in sync with that particular concept. So what is the question? The first question is from this graph, you have to calculate what is the value of A. And the second question, what is the pressure on this shaded area? So guys, you can give it a proper try for a few minutes. It may take up a few time also to solve this question, and then come back to see the solution. So I hope you have given it a fair try. Let's go to the solution of this question. So I have drawn the same velocity distribution graph here, and from the statement itself, it's obvious that if it is fx, and I have taken a very small rectangular strip here at a distance vx, and the thickness of the strip is dvx, then the area of this shaded portion, which is fx into dvx, and this area gives us the fraction of molecules that are moving in a velocity range from Vx to Vx plus dVx. Right, guys, it is a very similar fraction that was also used in Maxwell-Boltzmann velocity distribution graph and speed distribution graph. Only there the fx function was not that simpler. The fx was a complex function. So in this hypothetical model, I have simplified the function fx so that we can solve the question easily, or we can calculate them very easily. Otherwise, the question or the concept is very similar to the actual Maxwell-Boltzmann distribution graph. Now, very important question can be asked from Maxwell-Boltzmann distribution or speed or velocity distribution graph, that can we find the number of molecules that are moving with exactly Vx speed or exactly Vx velocity? And the answer to this question is zero, because this entire chapter is actually a statistical mechanics, you can say, where everything we define is based on the probability. So how many possible velocities are there for any gas molecule? So the answer of this is infinite, because the gas molecules can take any velocity from minus v naught to plus v naught. And if I ask you what is the probability of a gas molecule having a velocity exact vx, then it will be 1 divided by infinity. So the probability is 0. So that is why the answer will be 0. Yes, but what is the number of gas molecules that are moving with a velocity range, means from Vx to Vx plus dVx, that you can calculate from this function. So that is what the function actually says. Now you can understand from this graph is that if I integrate this entire area, or if I find the area under this graph, then that will eventually say that the fraction of molecules that are moving with a velocity from minus v naught to plus v naught along x-axis, and that fraction has to be 1, because no other velocity is possible for this gas molecule along x-axis. So I can simply say that the area under this graph is 0, and I have calculated the fx function. We can use it later. Vx positive, the fx function is a simple straight line function, and the area under this graph is integration of that, or you can simply say that it is the area under this triangular portion, which is 1, and from this equation I can easily get the value of a, which comes to be 1 by v naught. So that is the answer of your first question. I hope you have understood why I have made it 1, because the fraction itself will be 1. No other velocity is possible other than this one along x-axis. According to this question statement, you can definitely say the fraction is 1. Now the next question is the pressure on this particular wall. So I have taken this wall, the cross section of this wall, and on the left side of this wall, there are so many gas molecules present. You can imagine that all the gas molecules are having different velocities in different directions. But I can say that I'm only focusing on the X component of these gas molecules, because it is only the X component of the gas molecules that are going to change after each collision with this vertical wall. Because this is on the right side, I can say it is our x-axis. This is our x-axis on the right side. Uh, so I can say that only we will focus on the x component of the velocity of the gas molecules. And more specifically, let us take a specific case where the gas molecules are moving with the x component velocities having varying from Vx to Vx plus dVx I cap. So now I am considering a particular type of gas molecules only, those which have the component of velocity along x-axis from Vx to Vx plus dVx. And I'm trying to understand that how many such molecules are going to collide with this wall in next 1 second. So for that, I have taken this cylindrical region where the area is unit. This area I have taken to be 1, this area to be 1, so that I can directly find the force per unit area. So this is area, and this is the length of the cylinder, and I can claim that if the length of the cylinder is Vx, then whatever molecules are present inside the cylinder having this property, means the molecules are having the x component velocity from Vx to Vx plus dVx. So these molecules are going to collide with this particular wall in next 1 second, right? That is my claim. I hope you can understand. I have written also here. Now in next 1 second, only the molecules with velocity Vx I cap and Vx plus dVx I cap inside the volume uh, drawn in the pink color will hit the plane elastically. And what is this number? This number can be easily found by this one, n into area is 1 into Vx, that is the volume. This is the volume of this pink color container, and n is the number of molecules per unit volume for this gas molecules. So n into this volume is the total number of molecules present inside this container. Now from the graph given, from this velocity distribution graph given in your question, you can say that if I multiply this number with this function fx, f of vx dvx, then this is a fraction and this is the actual number of molecules. So if I multiply, then I can claim that this is the total number of molecules present inside this container, inside this pink color cylinder, which are having a component of their velocity along the x direction from Vx to Vx plus dVx, and where n is the number of molecules per unit volume. So these number of molecules are going to hit per second per unit area on this particular surface. And we know that for each molecule, the change in the momentum after each collision is 2 mvx, because it is an elastic collision. So for each mass m, if it is moving with vx, it is also other component of velocities, but they are not going to change because this plane is perpendicular to x-axis only. So after collision, elastic collision, this mass is going to come back with a minus vx velocity. So the change in momentum, its magnitude will be delta p is 2 mvx. And this change in momentum is happening per second on this wall, and that is going to give the force on the wall per unit area, and that is nothing but the pressure that we have to calculate. So 2 mvx is the change in momentum for each molecule. So for this number of molecules, what is the change in linear momentum per second? That will give me the pressure at that particular wall. So I have taken this number here and multiply it with 2 mvx, and then I have integrated it from 0 to v1, from 0 to v naught. Now, why I have not integrated it from minus v naught to plus v naught? The reason is simple, because few molecules will be present here which are moving along positive x-axis, and definitely few molecules will be present which are moving along negative x-axis. So I will not take the molecules which are moving along negative x-axis because they are not going to collide with the wall anyway. And only the molecules moving along positive x direction are going to collide, and that is why I have taken it from 0 to v naught. Remember, the graph has both the sides, but I will not take this side because it belongs to the molecules moving along negative x-axis. I will only take the molecules moving along positive x-axis. That is why I have integrated it from 0 to v naught. So that will give us the answer of this question. Now in next page, I will just solve mathematically what is the expression for this calculation. So 2mn and fx vx square dvx. Now I have put the value of fx that already we have derived in our first slide. A into 1 minus vx by v naught into vx square dvx. Then I have integrated it from 0 to v naught. And this is a very easy calculation. You can do it by yourself. And the final answer that we have got is rho v naught square by 6. So I hope you have a good idea of how to find the pressure on any wall from this Maxwell-Boltzman velocity or speed distribution graph, and try to understand it in a better way. I'm not suggesting you to remember or memorize the big expression of that function. It is not required, or nor it is in your syllabus. But you can understand the technique, or you can understand how we use that information, or how do we use that graph to calculate the pressure. So I have a bonus question for you. A gas follows all the properties of ideal gas except it follows a hypothetical speed distribution graph. So it is a speed distribution graph, and now you can say that if v into dv will give you the fraction of molecules that are moving with a speed from v to v plus dv. So with this information, you have to find the value of a and what is the RMS speed of the gas. So try to solve this question and send me the answer in the comment box. And if you like this video, then please hit the like button and don't forget to subscribe this with your friends. Thank you.